In this lesson, we're going to look at rules that tell us what it means when we add and multiply probabilities. So the rules we'll cover are simplified versions of the rules for conjunction and disjunction. And we'll see that since they're simplified rules, there are special conditions for applying them. So our aims will be to introduce these rules for calculating the probabilities of complex sentences, ones that contain disjunction and conjunction under the relevant circumstances. And then because they're relevant to the conditions, we're going to clarify the distinction between mutual exclusivity and independence. The condition for our first rule for today is mutual exclusivity. So remember, two statements are mutually exclusive if and only if they can't both be true together. So some sentences are mutually exclusive or mutually inconsistent as a matter of logic. Remember our inconsistent sentences from when we looked at truth tables and proofs. And examples would be a sentence and its negation. Those are mutually exclusive. Some sentences are mutually exclusive as a matter of fact, not of logic. So logically, it's possible for sugar to be fully dissolved and sugar to be in a cube at the bottom of a cup. That doesn't obey any of our rules about the logical connectives. But you should recognize as a matter of fact that it's impossible for sugar to be fully dissolved and be a cube at the bottom of the cup. Those are not mutually compatible states of sugar. So those two sentences describing those states are mutually exclusive. With the property of mutual exclusivity in mind, we can give a rule for the probability of the disjunction of two mutually exclusive sentences. So if we have the sentences P and Q, and we know that P and Q are mutually exclusive, then the probability of the disjunction P or Q can be given by the probability of P plus the probability of Q. How can we make sense of this rule? Note that because of the mutual exclusivity condition, this rule only applies when only one or the other of the disjuncts is true. So it doesn't apply in cases when it's possible for P and Q to both be true together. Since P and Q are mutually exclusive, there's no overlap in the circumstances that make P true and the ones that make Q true. And we see that in the diagram given here. The orange circle is the circumstances that make P true, the green circle is the circumstances that make Q true, and because there's no overlap in the circumstances that make the sentences true, these sentences are mutually exclusive. Remember too that P or Q is true as long as at least one of the disjuncts is true. So if P is true, the whole disjunction is true. If Q is true, the whole disjunction is true. It just happens to be that because of this mutual exclusivity property, these disjunctions won't ever be ones where both P and Q are true together. Then we can ask, okay, what's the chance of one of these sentences, P or Q, being true? We'll take that brown box to represent all the possible circumstances. The chance of P or Q being true is the chance of falling within just one of the circles. So you can fall in the P circle or fall in the Q circle. And the chance of falling in one circle or the other, since you have those two options, those two sets of circumstances, that chance is larger than the chance of falling in just one circle. If you want a kind of visual metaphor, imagine you're trying to throw darts in that box, and you're not very good, but you can get it in the box. You're more likely to hit P or Q than you are to hit just the circle for Q, for example. So we've rationalized what this rule means and tells us. Let's look at an example. What's the probability that it is snowing or cold and cloudy in New Brunswick. And we'll take the probability that it's snowing to be 0.05 and the probability that it's cloudy with no precipitation to be 0.5. First, we have to assure that the statements in the disjunction are mutually exclusive. If not, we can't apply our simple disjunction rule. So, are the circumstances described by it is snowing and it is cloudy without precipitation exclusive? Yeah, snow is precipitation. So these two circumstances cannot both happen together. They're mutually exclusive, and we can apply our simple disjunction rule. For that, we need the probability of S, that it's snowing, and C, it's cloudy with no precipitation. So S is 0.05, and the probability of C is 0.5. And our rule tells us that the probability of S or C is the probability of S plus the probability of C, 0.05 plus 0.5, or 0.55. Our next rule applies to conjunction. And the condition for applying this rule is independence. So remember that two statements are independent if and only if the truth of one statement does not depend on the truth of the other. Independent statements have to be distinguished from mutually exclusive ones. So independent statements shouldn't be mutually exclusive, except under one condition, when the probability of one of the statements is 0. Unless that's the case, there has to be some overlap between independent statements. If you find out one statement is true, though, that shouldn't affect your judgment of whether or not the other statement is true. That's what independence means. So if you have two sentences, P and Q, and you know that they're independent, then we can get the probability of the conjunction of P and Q. And that's given by the probability of P times the probability of Q. How can we motivate this rule? Well, since P and Q are two sentences that were conjoined, they're supposed to be independent. When that's the case, there can be overlap in the circumstances that make P true and the circumstances that make Q true. P and Q, the conjunction, can only be true when both P and Q can be true together. So we see that in our diagram. I'm giving the statement that they're independent, though sentences can have overlapping circumstances when they're true, even when they're not independent. But we're saying that these ones are. So stipulate that P and Q are independent. For the conjunction to be true, there has to be overlap between P and Q. And if they're independent, there should be. Then we have to ask, what's the chance of both P being true and Q being true together? Well, if the box represents all the possible circumstances, some where neither sentence is true, the ones in the orange circle are the ones where P is true, the ones in the green circle are the ones where Q is true. We want to know when they're both true, and that's represented by the overlap in the two circles. So what's our chance of landing in that overlap? That's the probability that both statements are true. Before we look at an example of the simple conjunction rule, let's go over a few more examples to get clear on the distinction between mutual exclusivity and independence. Getting clear on this distinction is essential to knowing when we can apply simple disjunction and when we can apply simple conjunction. So what's happening in this table is that each of the rows contrasts pairs of statements on the same topic. The pairs on the left are mutually exclusive, and the pairs on the right are pairs that are independent. So these two statements are mutually exclusive. The die landed 4 on the first roll, and the die landed 6 on the first roll. You can't roll both of those numbers in a single roll. That's just how rolling a die works. On the other hand, these are mutually compatible and independent. The die landed 4 on the first roll, and the die landed 6 on the second roll. There's no reason that those both can't be true, and what you roll the first time doesn't affect what you roll the second time. So those statements are independent. Now let's look at the next pair. The sentences Jamie has blue eyes and Jamie has brown eyes are mutually exclusive. It's impossible for both Jamie's eyes to be blue and for them both to be brown. That's not how eye color works. But it is possible for Jamie to have blue eyes and Jamie's sister to have brown eyes. So those two statements are mutually compatible, and they're also independent because what one sibling's eye color is doesn't affect the eye color of other siblings. They're both affected by similar circumstances, but they don't affect each other. That's what makes them independent. And finally, our last pair of mutually exclusive statements. The painting is genuine and the painting is a forgery. Those can't both be true together. It can either be that it's genuine or that it's a forgery, but it can't be both. On the other hand, if we imagine a collection of artworks where the paintings in the collection are genuine and the sketches in the collection are forgeries, those are mutually compatible and they're independent. The fact that the paintings are genuine doesn't make the sketches forgeries. We can determine the truth of those statements independently from each other. For now, we're relying on intuitive judgments to determine whether the truth of statements are independent of each other. But it is sometimes not so easy to tell. For example, is a weather event that happens on one side of the planet independent of a weather event that happens on the other side of the planet? We may not be totally sure. So in upcoming lessons, we'll actually see that in cases like that, where it's not obvious whether the statements are independent or not, we can use other ways of getting the probabilities of those statements being true to make judgments about whether or not the statements are independent. So here, we're moving from independence to the probability of a conjunction. And in future lessons, we'll look at moving from probability judgments to judgments about independence. A bit of the reverse of what we're doing now. So now that we've got hopefully a pretty clear sense of this distinction between mutual exclusivity and independence, we're ready to determine whether we can apply our simple conjunction rule to this example. So here's the example. Take two siblings. What's the probability that one has hazel eyes and the other has brown eyes? If the probability of them inheriting hazel eyes is 1/3, and the probability of them inheriting brown eyes is 1/2. First, we have to do our check. Are the eye colors of the two siblings independent? Remember, what matters for independence is the truth of one statement doesn't affect the truth of the other. Well, we've already looked at this. Eye color of one child doesn't affect the eye color of another child. Eye colors are independent. And since they are, we can use our simple conjunction rule to determine the probability of both of these statements being true together. So H is one child inherits hazel eyes, B is the other child inherits brown eyes. Since we know those are independent, we can use the probabilities of those simple statements to determine the probability of the conjunction. So the probability of the conjunction H and B is equal to the probability of H times the probability of B. The probability of H was 1/2, and the probability of B is 1/3, and we multiply those to get 1/6. So 1/6 of the time, imagine if we're repeating possible cases where children are born from these parents, 1/6 of the time the children would have one with brown eyes and one with hazel eyes, or there's a 1/6 chance of this being how the children turn out. Now you have in hand 5 rules for determining the probability of complex sentences. And in the next lesson video, we will introduce 2 more, one for negation and moving to another rule, this time a general rule for disjunction, instead of our simple rule with a condition.